Okay, so we want to look at the period and frequency as a function of mass and spring constant, so M and K. And we know that for a vibrating body, the restoring force, F is equal to MA, which is also equal to negative KX, so that's nothing new. We know that F is equal to 1 over 2 pi squared of K over M, and T is equal to 2 pi squared of M over K, and there's no derivation that I've given for this, so we're just going to go with that, and I can show you if you'd like to know. The frequency and the period can be found if the spring constant and the mass are known. Make sure you're consistent with your units. Newtons per meter and kilograms is the best thing to do. That way you stay out of trouble. So pause and get those recorded. All right, so the frictionless system shown below, so that means we're going to have conservation of energy available to us, has a 2 kilogram mass attached to a spring. That's the spring constant. We're going to pull it over 20 centimeters to the right, and we're going to release it, and we want to know the frequency of the motion. Well, frequency is 1 over 2 pi times the square root of K over M. K is 400. M is 2 kilograms. So 1 over 2 pi times the square root of 200 gives us 2.25 hertz for our frequency. So pause and record, pause and work through it. Okay. So Foucault pendulum. So now I want to talk about pendulums. Is a tall pendulum free to oscillate in any vertical plane. The direction along which the pendulum swings rotates with time because the Earth is rotating with time as we go through our day. I think there's a lovely one of these at A&M in the physics building. All right, so the simple pendulum. The period of a simple pendulum is given by T is equal to 2 pi squared of L over G, where L is the length of the pendulum and G is gravity. Only works if we keep our angle less than 15 degrees. So that's what it means by the small angle theta. You need to stay 15 degrees or smaller. All right, if this is my period equation, then the inverse of that would be my frequency equation. What must be the length of a simple pendulum for a clock that has a period of 2 seconds? So if I know the period and I'm looking for the length, I'm going to go ahead and just rearrange that little rascal. And when I do that, I get L is equal to T squared G over 4 pi squared. So I know my period is 2 seconds. I'm looking for the length. So that's my length of my pendulum. All right, so let's look at this. It says a pendulum is 1 meter long and is set into motion. The mass of the pendulum bob is 0.5 kilograms. The period is calculated. The pendulum is set into motion and the calculated period agrees with the measured period. They take the bob off and do it again. What's the period of the pendulum? So what I know is that if my period is equal to 2 pi square root of L over G, nowhere in there does it mention the need to have the mass of the bob, so the period's not going to change. So my new period will equal the period that was calculated and measured. All right, and I think if you do that, you get 2 seconds. Pretty darn close to 2 seconds, okay? So we're just trying to make sure that you understand that changing the mass doesn't change the period at all. The only thing that changes the period would be the length of the string or the gravitational attraction. The longer the string, the greater the period. They're directly related. Okay. All right, so I give you some pendulums. 1/4 of a meter, 0.37 meters, 0.69 meters, and 0.86 meters. I want you to rank the pendulums in the order of their period from greatest to smallest. So how should they be ranked if the student would like to be correct? Well, we've already just said that T is equal to 2 pi square root of L over G. So the greater this is, the greater that is. So this one's going to have the greatest. And then this one, and then this one, and finally this one will have the least. L-E-A-S-T. And if you think about a little short pendulum, it makes sense. It's not very long. It doesn't take very long for it to complete its cycle. But if I have a very long pendulum, it's got to go all the way over and back. So that's going to have a much greater period. Conceptual, not a big deal. You got it. Okay. All right. So on Monday, we're going to do our pendulum lab, which is our formal lab. I've given you a little handout. Get that ready this weekend. And then this should say on Tuesday, we'll do Hooke's Law lab. Okay? Now, we've got a couple of problems here. And I'm going to let you work through that one. And that one. And that one. and we will check them when I see you on, probably on Wednesday we'll actually check them. Have a great weekend.